Leon has a huge number of slides, so I'll keep the introduction really short. It is my pleasure to introduce Leon Hirth. Leon is a professor at the Hirth School of Governance, among other affiliations in Berlin. Previously was with the Swedish utility Vattenfall for a number of years, and his work over the last several years has been really great, and certainly some of us working in the electricity markets and policies group have used it as inspiration for some of our work, and perhaps the reverse is also to a limited extent true.
Not a limited extent, yeah.
Right, so I'm looking forward to turning it over to you. We do have until the top of the hour. I imagine you'll accept at least some Q&A during the course of the presentation, but at some point you'll want to just get through slides too. So feel free to just control the room as you wish, but otherwise people should feel free to jump in with any clarifying questions, I think, at least during the course of the presentation, unless we get too far behind schedule. So Leon, take it away.
Thank you very much for the kind introduction. I can really say I'm honored being here. It's great having that I can be here and meet all you people. It's very true. The work that you've been doing here at the lab has inspired a lot of my work, and I think it's fair to say I wouldn't be doing what I'm doing if it wasn't for the work that you've published. I want to talk about the market value of wind and solar energy. It's a long slide deck that is building on a series of papers that have been published over the last 5 years or so with a number of co-authors. I'm happy to share the slides. Managed to send over the PDF afterwards, so there's stuff that you can go and flip through if you'd like to. On a subset of the slides we believe to be most interesting for this audience of you, and I invite you to jump in and discuss and ask all the time. So let's keep this interactive and let's make this a conversation. So I don't think I should run through the slides in the end, but let's discuss things as they pop up. This is what I did not too long ago. I mean, I wasn't operating that machine personally, but I was working with a company that does open pits lignite mining, low-grade coal mining in Germany. Since then, I've been working with my own consulting firm, advising the German government, the EU Commission, and the private sector. And starting this year, I have a position at a public policy school called Hirth School of Governance in Berlin. My interest is around electricity markets, renewable energy, economics of wind and solar in particularly, and numerical modeling. So there's a lot of overlap with work that is done in this place. Let me start with the motivation, how I perceive many policymakers that come more from the climate policy perspective see renewable energy. I think a starting point that they come up with is that we need to prevent dangerous climate change. We really need to bring down greenhouse gas emissions by mid of the century to very low levels. It seems to be easier to do emission reductions in the energy sector than elsewhere. In particularly, agriculture is very difficult. Within the energy sector, electricity seems to be easier in terms of abatement than other sectors, in particularly transports. Plus electrifying transport and the heating sector will drive up demand for electricity. In other words, the power sector needs to reduce emissions and at the same time increase outputs, sort of as a global high-level storyline. How that can be done? Well, there's essentially 6 large-scale options available globally to produce low-carbon electricity: nuclear, CCS, biomass, hydroelectricity, wind and solar. And for various reasons, at least in Europe, nuclear is good reasons maybe is out of fashion. CCS is not really accepted. Biomass is competing with food and other products, so it's likely to be difficult to do this on large scale. And hydroelectricity, of course, is constrained by the geology and geography. So what really is there is wind and solar as scalable, low-cost, low-carbon generation technologies, which led Mr. Energiewende, Rainer Barke, to say that the Energiewende is all about wind and solar power. And that's, I think, a fair summary, even though it's 4 years old. It's a fair summary how policymakers still see the game in Germany. Being from Germany, I brought you a few numbers. This is the increase of renewable electricity generation in Germany. We are currently scratching at the 35% penetration rate on an annual basis. And wind and solar alone has generated about 21% of electricity last year. 2017 is going to be quite some more, maybe 25%. Comparing to other countries, that's a lot, but there are countries that produce a lot of more electricity from wind and solar, fluctuating sources. If you look at countries, Denmark is leading the crowd, and the countries on the Iberian Peninsula also have high shares. Ireland has a lot of wind, and then Germany comes fifth. If you look at power systems, subnational jurisdictions, you have also a few of US states would be up in the list. I think Iowa has 25% or so wind. I heard last night. Globally speaking, during the last years, this is slightly outdated data, but it's looking even better the last 2015 and 16. Globally speaking, half of all new added capacity globally was based on renewable energy. This is data from the IEA, and wind and solar took the largest share of this. Let's look at solar and wind costs for a bit. I'm going to be brief here because I promised you to talk about value, but let's start with cost. This is a figure put together by the IEA in the medium-term renewable market report. This is results of renewable energy tenders, and what you see here is a number of tenders where bidders promise to produce electricity to deliver renewable-based electricity at really low prices. So we talk prices as low as 25 euros, but a number of auctions, large auctions globally have resulted in prices between $40 and $60 per megawatt hour, which is incredibly cheap compared to what we saw only 5 years ago or 10 years ago. And that's true for wind, both onshore and offshore, and solar PV. Why are prices so much lower than they used to be 5 years ago? The most important answer is that equipment has become cheaper and more reliable. But the second important answer is that renewable is a investment-intensive business, right? You build them, and that's the investment, and then there's hardly any more cost. There's no fuel cost, no emission certificates, or any other variable cost during the lifetime. So it's a capital-intensive business, and luckily for renewable energy, we are living in a low cost of capital environment. Interest rates are lower than they were ever, real interest rates in the last 50 years or so, and that has helped renewables becoming cost competitive versus other technologies dramatically. But that also means if interest rates going to pick up again, and they might actually pretty soon, renewable energy will suffer more from that higher cost of capital than other technologies. So that's a trend that can, of course, also be reversed. The next 4 slides go through these items here, and I'm going to skip them. You can have a look if you're interested afterwards, sort of giving you some underlying data about equipment on cost of capital and competitive factor trends that helped bringing down costs of renewable energy. The point that I really want to make is that cost is only half of the story. If you're interested in the question how much renewable energy is going to be there in the long term, the economic answer is, well, there should be as much to equate the marginal cost and the marginal benefit of renewable energy in a socio-economic sense. So this is if you took an Econ 101 course, that's the type of figures that economists use to confuse other people. So the optimal deployment level is determined by this intersection, and if costs come down, the optimal deployment level increases, but it's still co-determined. It will always be co-determined by the marginal benefit of renewable energy. And that's what I would like to talk on more. So a lot of my research is focused on the question, what is the economic marginal value of wind and solar energy, and what can we do about it in terms of like giving it a higher value from a policy perspective, and what are the implications for market and energy policy. So let's talk about value. The easiest way to start this is with a simple observation that I believe everyone here is well aware. This is a snapshot of, in this case, German market data. That's the so-called day-ahead electricity price, electricity market, a snapshot of 5 days. And what you see is prices are sometimes low, sometimes high, sometimes zero, sometimes negative. That implies by itself that if you want to say anything about the economics of a specific generation technology, you need to know when it is producing electricity. Obviously, if you have a generator that only produces at negative prices, even if that generator was free to buy, you wouldn't buy it because its net benefit would be negative. Looking at German data, in 2001, that's the first year after liberalization of the market, the average electricity price was the base price is called was 23.1 euros per megawatt hour, and the average income of wind turbines in that very same year was 22.7. The ratio of these two I'm going to call value factor, and I'm going to use that term quite a lot. The value factor I define as the income of wind turbines divided by the average electricity price. So in 2001, wind farms earned on average 96% of the average electricity price. Fast forward 15 years, base price 29, revenue 25, so wind farms earned only 85% of the average electricity price. If you put that on a figure, you're going to get this. This figure shows market share of wind in blue and solar in yellow of the last 16 years in Germany in annual energy terms, and that's the same value factor. So that's the revenue of the respective technology divided by the average electricity price of that year on wholesale markets. And what you're going to see, what you obviously see here is a negative correlation. So as the wind penetration increased, the average income of wind farms in relative terms declined, and the same was true for solar energy, just at a more dramatic speed. So if you extrapolate these figures and just think about what that means, well, the more renewable energy there is in the market, the less it's worth. And if these trends would continue, you would get to very low values, very low revenue levels at quite small penetration rates, which would really jeopardize the decarbonization and transformation of energy systems globally. Yes, please.
To clarify that, the price actually went up, or the value went up, but in the proportionally it went down. So is one of the reasons because early customers locked in the price? I mean, that's one of the attributes of renewables is you can pay a little bit more now, but you lock it in for the life of the system. So wouldn't that fact create the same issue that as the price of energy goes up, the spread between now what I'm paying because I bought it 10 years, I locked myself into a contract 10 years ago, wouldn't that have the same effect? I mean, you're sort of implying that the value is going down. To me, the value stayed the same, it's just that the price went up.
So when I say value here, I really mean revenue, what you can earn if you sell your electricity. Assume you own a solar plant and a wind farm, like you, and you sell the output to the wholesale electricity market. That's what pretty much every commercial actor does. And this shows here what you would earn. It doesn't show you the number in dollars per megawatt hour, but in relative terms. That's because you're partially right. Electricity prices overall, on average, increased wholesale prices between 2001 and 2008 when they peaked, and they declined since then. So there was a huge boom-bust cycle and some sort of smaller hiccups in between. And to sort of cancel these fluctuations, these more macroeconomic fluctuations out, I divided one with the other. So, what this figure shows is compared to the other electricity generators, wind power earned less and less over the course of the years as their penetration rates increase. And on the mechanics, why that's the case, I think the simplest way.
Well, at the same time, in this period of analysis, there were declining prices of many fossil fuels that could have been also the marginal units, right? So how can you tease out that element? That's
captured in the average electricity price. So if let's say if all costs of all fuel costs just decrease by 50% and nothing else happens, sort of a deflation of commodity prices, then this would be cut by half, this would be cut by half, and you would end up at a stable value factor. That's precisely why I report value factors and not absolute levels, because I'm not interested in fuel price fluctuations. I'm interested in the patterns of electricity prices that determine the competitiveness of wind and solar versus other fuels. Of course, overall fuel levels, cost levels also matter, but it also matters how wind and solar perform in revenue terms vis-a-vis other technologies. Let me try to explain what I think is the mechanics behind that, or the easiest way to explain the mechanics behind that. We use a tool that Europeans call the merit order curve. You can call it the supply stack curve, or just the short-term marginal cost curve. That's the capacity that's roughly modeled after Germany. That's the installed capacity of different power plants in Germany. So this would be 80 gigawatts. And wherever demand is for a specific hour, I assume, realistically, I believe that electricity demand is on the short term is price inelastic. So the electricity price on the power exchange or on the market is determined where marginal cost interact with demand that results in the market clearing price in a specific moment of time, let's say in the first hour of the year. If in that hour of the year, additional wind supply comes into the market, the net load, which is loads minus wind and solar generation, is reduced, and this net load is the load that needs to be served by conventional power plants, and with reduced net loads, the price is reduced. In other words, whenever there is wind added to the market, wind power added to the market, in that specific moment of time, the price is compared to the same hour if there wasn't any wind. Systematically, wind eats up its own price, if you'd like to say so, an effect that my former boss used to call the self-cannibalization effect. I'm not sure if that's the nicest term. In essence, it's just simple economics. If you increase the supply of the goods, its relative price goes down. In this case, the goods under consideration is wind energy or solar energy, and that makes it a little trickier to observe. And obviously, the shift here is larger if you have more wind turbines installed in that region. So whenever the more wind power is installed, the stronger the shift of the price decline in windy hours is, and that as a consequence results in the pattern that you've seen, that on average of the course of a year, the income declines with higher average penetration rates. So far, the bad news. I said if you would extrapolate that trend, that linear trend, the picture would look pretty bleak, but of course extrapolating a historical trend is something you should never do if you want to take sensible decisions. So what we did here to understand how this pattern evolves in the future is use a very simple numerical electricity market model that covers these regions here. It's a pretty simple but relatively standard electricity market model that also model investments. So it's a greenfield model. Under certain conditions, the model determines the cost of electricity mix for Europe, both in hourly dispatch and the investment in power plants. The model is open source, so you're invited to have a look and run your own model runs if you want to verify what I'm going to say now. So what we do here, what I show here is results that hold for this region of European countries, and the figures have the same structure. We have the wind market share in yearly terms on the x-axis and the value factor on the y-axis. So the dots that you saw before cover that range here, and what this model suggests is that the value continues to decline with increased market share, not as steep, not as much as up here, so it levels off a little bit, but the decline continues. What does the number mean? The number means that at 30% wind market share, the value of each megawatt hour of electricity from wind is 40% less than the value of the first megawatt hour. There was only one single wind turbine installed. And that's quite a dramatic decline. For solar power, the picture looks even worse. Here, increasing the value share, the solar market share to 15%, we observed a 50% drop. So each megawatt hour of solar energy is worth only half than it used to be. Where does the difference from wind and solar come from? Well, let's compare this first with observations. So and that's a figure that's sort of these model results come out of a 2013 paper. So this was something I did last week, and I overlaid the model results with historical developments. And some of these observations obviously happened after the publication of the paper. So it's a good test to see if the paper sort of serves if you tested with data that was only merged after the publication. And at least so far in this range, we are able to hit German data pretty neatly, I'd say. So the observations and model results seem to fit. Where does the difference in wind and solar come from? Sorry, there's a slide. I didn't bring that slide. So there's obvious solutions to that problem if you perceive it as a problem. Electricity storage is one. It's pretty clear if you had unlimited electricity storage that was at 100% round trip efficiency, electricity prices would be flat all the time, right? There wouldn't be any price fluctuations because they would all be, if there were any fluctuations, people would store and generate electricity, and so the fluctuations go away. But we don't have unlimited priceless electricity storage at 100% efficiency. Storage is limited and costly and has losses. So what we did here, we tested the impact of doubling European existing pumped hydro storage capacity. So we did 3 model runs. The first model run, and you already saw this, was having the existing capacity in place. Second model run have no capacity in place. And the third model run was having double existing capacity in place. And the impact is as expected. If you have more storage, then the value of wind, or in this case solar energy, in this case wind energy, is increased. But the key point here is that the impact is relatively small. So even if you double existing pumped hydro capacity, which is quite an investment, you still have a relatively limited impact on the value of wind energy. If you increase interconnection between countries, you get a similar effect, a little more. That is, of course, because there's geographic smoothing effects. Sometimes there's wind in France, but not in Finland, and sometimes in Sweden, but not in Switzerland. And so if that can be traded more easily, then things are smoothed out, which is good for the value of wind energy. But still, overall, it doesn't qualitatively change the picture.
Have you tried to quantify the current relationship between wind and solar? I mean, if a rise in solar also affects the value for wind or vice versa?
It does. The impact is relatively small according in the data that we use. I don't have the picture is in the paper, but not in the slide deck. Or I show you a slide that's related in a bit.
How low is the pumped hydro storage capacity? Because if it's very small, doubling it, maybe you can get much more. I'm not asking for numbers.
Yeah. I think installed capacity is something like 20 gigawatts in a system that has a peaking capacity of all countries together, 250 maybe. And they are relatively small volume hydro storage. So they are relatively small basins. So 6 hours, 8 hours of storage, not more. So you're absolutely right. If you change with the solar ratios, and if you change anything in the model, that's going to impact the results. And so everything has an impact on this value. Fuel prices, the combination, the amount of storage, the price of CO2 certificates, and any other things, interconnector capacity. So what we ran a lot of sensitivity analysis, and that's sort of the parameter uncertainty range that comes out of this, again, for wind value factors. We believe the value of wind energy in Germany to be 0.5 to 0.8 of the average electricity price at a market share of 40%. And this is the dotted line is the same dotted line that you saw before, sort of our best guess parameter model run. Yes.
Is the average value factor across all energy sources equal to 1, and therefore, as wind and solar lose value, there's other sources that are gaining value, and if so, what are those?
It's not exactly 1, it's a little higher.
The average is higher than 1.
The average is higher. You would get a value factor of 1 if you had a baseload plant that runs 24/7. So a nuclear plant has a value factor of almost 1. But because there's peaking plants in the system, that disproportionately, a peaking plant produces disproportionately at times of high prices, right? So a peaking plant might have a value factor of 2 or 5 or maybe even 10. So the average is slightly above 1. The average in this region is maybe 1.1.
So that's essentially a storage technology, right? I mean, the fuel is being stored, so it's a different storage technology that's winning the market from a value standpoint.
You can see it like this, yeah. I mean, depending how you define storage, but yes, in that sense, yes. In the sense you phrased it, yes.
Is this wind market share before or after potential curtailment?
In this model, there is no curtailment at this level, so that it wouldn't matter. Also, for the calculation, it doesn't really matter. This model has a little more flexibility than reality. So in this model, you would only curtail wind if you have prices of 0. And if you have prices of 0, your income is 0, regardless if you curtail or not. So it really for the income side doesn't matter, but of course it matters for the denominator of the equation, what's the market share. And here there wasn't significant curtailment taking place. Even for solar. Solar, we only report up to 15%. 30% solar, 15% is by and large still fits into the system. I think this is reported after curtailment. So really, in terms of usable energy, 30% of the consumed energy is coming from it. We checked with a number of other studies. Each line represents one study. Several of these lines represent work done here at this lab, comparing different geographies and different methodologies, and that by and large they all conclude that the value of wind energy is declining with market share. Some forecast a very steep decline, some a more modest decline, but the decline is going to be there. So summing up these results, our market data, our own modeling results, and looking at the literature suggests by and large a consistent pattern, loss in market value of wind power as penetration increases. Let's continue. So we understand the drop in value of wind and solar power, but do we really? There is sort of a couple of follow-up questions that came out of this work and that I've been working on in the last couple of years. So there's 4 topics that I'd love to discuss. Due to time, I need to focus on 2. First is what's the impact of carbon pricing? Second, what's the impact of what we call system-friendly wind power? Third, what's the impact of hydroelectricity? And fourth, can we say anything in analytical terms about this phenomena rather than running computer models? You're going to get the slides of all 4 of these topics, so feel free to have a look. I'm going to focus on the first 2 for the next half hour. Let's have a look at carbon pricing. So when we ran this model for the first time, the dotted line that you saw implicitly or assumed a carbon price of 20 euros per each metric ton of emissions. I was interested in understanding what happens if you increase that carbon price, and my assumption was, of course, that a higher carbon price drives up the price of fossil fuel generators that should help the value of wind energy. We turned on the model and looked at the results and found the model was wrong. It turned out we were wrong. The model was right. What the model produced was an output that said at high carbon prices, the value of wind energy is reduced compared to moderate carbon prices, both in relative and absolute terms. How can that be? I'm gonna explain how that mechanism works. I'm not making the argument that this is sort of representing reality in appropriate ways. I just wanna point out a chain of causality and a mechanism here. And you can judge yourself to what extent that's relevant. I'm going to skip the slide and first explain what the mechanics is. So this is the same supply stack, a simplistic model here. So we have a market clearing price, and wind comes in and helps, reduces net loads, and the price declines. Same pattern as here. Of course, if you look at this slide more carefully, of course, the size of the price drop for a given size of the price drop, of course, it depends on the shape of the supply curve, right? If the supply curve is very flat, there's hardly any price drop. If the supply curve is very steep or very convex, then the price drop is larger. So what happens in the model if you include a carbon price of 100 tons per megawatt per 100 euros per ton? Well, recall that this is a long-term model, so it models the entire power plant fleet, not as it is, but it's a greenfield model that finds the least cost power plant fleet for a given assumption set, including carbon price. So if you increase the carbon price to 100, what happens is that nuclear power becomes competitive, which really wasn't before. So at 100 euros, you have a large nuclear fleet, and nuclear is very investment intensive, very cheap to operate, relatively cheap to operate, so has low fuel costs. So nuclear plants would bid at their fuel costs, and at the same drop that you saw before, the volume drop in net demand would lead to a much higher drop, much starker drop in prices because variable costs of nuclear are so low. And this has that sort of surprising result that the market value of wind is reduced by introducing carbon prices at high levels. But of course, that mechanism rests on the idea that you can actually install nuclear power plants and that they will be built as a response to the carbon price. If it's not nuclear, you could also pick carbon capture and storage. CCS has similar cost characteristics, or more broadly speaking, any other type of generator that's investment intensive, but then relatively cheap to operate. Any such low carbon baseload plants that might be built as a response to a carbon price has a negative impact on the market value, or can have a negative impact on the market value of wind energy. And that's a surprising mechanism that I think I wasn't expecting at least. Put differently, wind and solar as variable electricity generators do not really go well hand in hand with baseload plants that need to run 24/7 to be economic. They go much better. They come much better along with generation technologies that are less capital intensive. Unfortunately, there aren't many of these less capital intensive, low carbon technologies available. Maybe biomass, maybe gas, natural gas, CCS, but the options aren't great.
To what extent does EMA look at flexibility requirements? So CCS and nuclear that you've picked as ideal investment vehicles have the disadvantage that they're not very flexible, right? And at increasing wind and solar penetration, you would need generation technologies that are able to ramp in order to actually accommodate those, which then will lead to a more steeply shaped supply curve and thus potentially mitigate the value decline. Is the model capturing that?
To some extent, the model doesn't capture something like ramping constraints from one hour to the other, but the cost characteristics of nuclear are enough, so the model would never build a nuclear plant that ramps up and ramps down, even though in the model it could ramp up and ramp down, but the cost characteristics are such that nuclear is only built if it's running to 85% of the time or more. Otherwise, there's a cheaper technology than nuclear in the model. So in that sense, while it doesn't have that feature, it still captures that effect. Okay, let's talk more positively about what we can do about this. There's a lot of things that can be done or that can happen to make this value drop less dramatic, to mitigate it. And this is grouped here into two parts. First, there's a lot of things that can be done at the level of the power system and market to make the power system more flexible, to accommodate more easily larger volumes of wind and solar energy. There's stuff like demand response, storage, more interconnection, making thermal plants more flexible, and shifting generation mix towards less capital-intensive plants, market design, using flexible hydropower to the extent it's flexible. And there's options at the level of the renewable energy technology and asset that can be done to make what we say the renewable energy asset more system-friendly. And one is obviously changing the geographic location and diversifying the mix. Like you suggested, having a mix of wind and solar rather than only wind and only solar is obviously going to produce better results. But here we want to look at something that's maybe less obvious, and that's so-called low wind speed turbines that have higher capacity factors. So what's this? What's system-friendly wind power? Well, first on that terminology, we call these things system-friendly renewables because they reduce what some people call integration or total system cost. Expressed differently, because they increase the economic value of the electricity that's produced, and they, as a consequence, might reduce the cost of support policies to deploy these technologies. So what is a low wind speed turbine? A low wind speed turbine is a turbine that combines two characteristics. That is, compared to a classical turbine, it's a higher power and has a larger rotor per unit of installed capacity. So think about two turbines here, and this is turbines that you can buy on the market. This is not fancy 22nd century technology, but a technology that's out there, and you can call Vestas, you can call Siemens, you can call Enercon and buy these turbines. So this is, I'm comparing here an Enercon 82 with installed capacity of 3 megawatts and the Vestas V100 with an installed capacity of 1.8 megawatts. You could pick other turbines these are just examples. And these turbines placed on a certain location in Germany would roughly produce the same annual output on electricity. In that sense, they are comparable because they yield the same amount of energy as an output. But they are different. The Vestas has a smaller generator, but a larger rotor. That's the diameter of the rotor. And the Enercon turbine has a smaller rotor and a larger generator. So whenever it's very windy here, the Enercon can produce at full speed 3 megawatts, and the Vestas obviously can only produce 1.8 megawatts because that's the rated capacity of the generator. If it's moderately windy, however, the Enercon is limited not by its electrical capacity, but by the amount of energy that can be harvested from the wind by the size of the rotor. And the Vestas, having a larger rotor, can harvest more energy. So the Vestas produces energy more energy at moderate wind speeds, and the Enercon more at high wind speeds. In other terms, if you compare two turbines that have the same rated capacity, this is normalized to 1, and different rotors, what we call an advanced or system-friendly wind turbine has a higher capacity factor than a classical turbine. These are real turbine models by the models we pick in this location that we use to assess these turbines. These specific turbines had a capacity factor that was almost twice as high. So this is slightly below 20% and slightly above 35%. The consequences of this turbine choice is that if you have a turbine, and I'm going to use this terminology, classical and advanced. Advanced means larger rotor, classical means smaller rotor. And these figures here show two turbine fleets that again produce the same annual output. So we're trying to compare apples with apples, to the extent that these are apples, that they produce the same amount of annual electricity. And the speed of advanced turbines has a smoother, less fluctuating output, because at high wind speeds, it produces less, but at moderate wind speeds, it produces more. So on average, it's more stable. The output pattern is more stable. That's also depicted on the right-hand figure. If you put this in the same EMMA model setup, you're going to get these numbers here. The dotted line is almost exactly the same line that you saw before. So that's the bold line is the bold line is what used to be the dotted line. So that's the classical revenue in value factor terms of a classical wind turbine, and that's almost exactly what you saw earlier. If you replace that fleet of turbines with turbines that are low wind speed turbines, you get a significantly gain in value factor. So here we, according to these estimates, we have a 15% higher value per megawatt hour of these advanced wind turbines. I want to repeat. We're comparing two cases here. In both cases, there's exactly the same amount of wind energy produced, just by different types of turbines. And in one case, every megawatt hour, each megawatt hour of output is worth 15% more than in the other case. That's quite a lot. there's quite some additional value coming in here because we produce in different moments and times. You can think about it as along the following lines. In some sense, a low wind speed turbine is shifting outputs in time. It's shifting output from windy times to moderately windy times, and thereby helping reducing the price depressing impact on power markets. Yes.
How does the capital cost compare?
That's an excellent question. This paper has focused on value, so we don't compare costs. In fact, a lot of these wind turbines have been developed because they're cheaper. Historically, they have not been developed because they have higher value, because in most countries, we're not at 30% wind, right? We all wish we were at 30% wind penetration, but we're not. We're somewhere here. And in this historical status quo, low wind speed turbines do not provide an additional value. Actually, they sometimes provide less value. So they obviously haven't been developed to get this additional value. They have been developed to reduce costs. So in some cases, it might actually be that this high value turbine is cheaper than this low value turbine. So you get lower cost and higher value. In other cases, it might be that it's a little more expensive, but it's worth paying this extra to get this higher value electricity out of the turbine. What the exact cost parameters are first depends on which turbine types you compare. It also depends on the site that you study, and it depends if you get cost data. And getting reliable cost data in this sector is notoriously difficult because manufacturers won't tell you.
Do you think the larger rotor diameters and higher hub height sort of the cost of those are offset by the smaller generator sizes?
I mean, reality is, of course, not that you would take one turbine model and install a smaller generator and a larger rotor. There's technology development, but the ratio changes. So it's sometimes expressed as specific rating, which is watts, electrical capacity in watts compared per square meter of area swept by the rotor. And that specific rating has declined, meaning less capacity per rotor area. So we used to have specific ratings of 500, which wasn't uncommon, and the US, tell me if I'm wrong, we are below 250, I think, on average. The drop in Europe is not that pronounced, but sort of an average normal turbine today has significantly less installed capacity per square meter of rotor area swept. I can't give you sort of good cost data. I can only sort of assume that a lot of that has been driven actually by cost reductions rather than value increases. And the point here is that that on top of that, you can expect, especially in high penetration scenarios, that these low wind speed turbines give you an additional benefit in terms of a higher spot market revenue.
In what terms do you consider how the wind speed is geographically resolved? Like, do you have different sites where you locate the turbines, or do you take like the same weather data for both turbines? Or
in that specific model, we used reanalysis satellite data for wind speeds, and then said we just assumed that wind turbines are built on all sites where we have on average, I think, 6 meters per second wind speed or so.
Okay.
And so we didn't resemble the historical patterns, but sort of assumed that on all good or moderately good wind sites, wind turbines are going to be built. And we have in different papers, we did it differently. It doesn't have a very large effect on this one here.
Because I would expect like smoothing when you also for the high-speed wind turbines when you install like one. Germany, that the effect isn't that strong anymore in comparison to the low speed.
You're absolutely right. What we did not do is sort of modeling all wind turbines installed at one site. We did incorporate geographic smoothing that to the extent possible in Europe and that's limited by the size of countries, by the interconnection capacity between countries, and by the fact that, well, wind conditions aren't great in Germany in most places. Yes?
Just a short question. Could you estimate the storage capacity that would need to be added to the grid to offset this effect? Because it doesn't seem like a good long-term solution.
That's interesting. First, the question is, I haven't done that, but you could do this. Sort of, you could, and maybe that would be an interesting exercise to say how much storage, like let's say we build classical turbines, how much storage would we need to build to have the same beneficial effect in this metric here? Have you done that?
No. But it's a good question, though.
You might will.
Maybe we will.
And the second comment that you made, that this doesn't seem to be a good long-term solution. Why?
Well, if you would offset it with storage and the price is played so that you would be able to do that, then you would not lose that additional power.
That's right, we lose it, but we lose it in moments of time when electricity is not worth much.
Yeah, but if you have a lot of storage, then the market is going to look differently.
But then you have to pay for storage. Yeah, of course, if storage
the assumption was
storage is very cheap. Yeah.
Or for some reason storage was
there. Which is a strong assumption, I would argue. I actually think this is maybe the best long-term solution that we have. Or maybe not, I mean, it's not the only solution. Storage will be part of the solution, but sort of of all the bits and pieces that we're going to use to obtain a higher market value, I believe this to be the single most important one. For wind. For solar it's different, but for wind I think it is. And it's true. I mean, if you talk to engineers, I come from an engineering company, and if you talk to engineers, I saw engineers that got angry at me with this, because they said it's so stupid. You're spilling energy, right? You're wasting energy. You could harvest much more, but you just don't use it because you install a generator that's too small. You can't transform it into electricity. And I said, well, yeah, that's true, but we're spending energy at times where no one wants it. We're spending energy at high risk times, and in this world, like electricity is going to be costly, but it's going to be for free in windy times. So spending energy in windy times is really something like spilling water when it's raining. It's not like spilling water when you're in the desert. And so it's technically speaking, it's a waste, but economically speaking, it's not.
Well, in Spain, we have a similar situation to that, but the difference is that we have a lot of pumping storage capacity, and you can see that trend too, because you can't avoid that storage have performance. I mean, it's 70 or 80% performance. So if you are producing 1 megawatt-hour, you only can use 0.7 or 0.8. So you are going to see that anyway. Probably not so steeper, but
that's not the only economic benefit that low wind speed turbines have. So what I presented here, you can call the increased value in bulk power that you earn from wholesale markets. On top of that, there's probably coming a benefit that you have reduced forecast errors, because these machines, it's easier to forecast the production of fleet of such machines, and you might also be able to reduce connection costs and grid expansion costs, because that is sort of, it's the capacity and not the annual output that determines some of these network costs. I think we have relatively robust numbers here, but we have only very rough estimates of those, so I don't give you the numbers because I don't think they're reliable. In the paper we speculated a little bit, but that's really guesswork. Overall, but I think the direction of the impact is clear that low wind speed turbines might be cheaper, might be more expensive, but they, at high penetration scenarios, they really give you an additional value from spot market revenues, and this comes on top of that. And that should be considered by investors. Well, is it considered by investors or not? That depends on policy and market design. I come from a country where for 15 years, renewable energy was just paid a flat rate, was just paid a feed-in tariff, regardless if it was high value or low value. And guess what? If you pay the flat rate, you just want to minimize production costs, right? So you find an optimal solution, and this is an illustration where you can, as an investor, you can choose specific ratings. You can choose, you can buy system-friendly or less system-friendly turbines, and well, what you can choose will only depend on cost. Turbine in LCOE terms, but that might not be the economically best option. Thinking of society, that might be another turbine. If this is the revenue or market value, and the market value represents the true socioeconomic benefit of the turbine, the best option would actually be this here, which is moved to the left, right? The optimal option is more towards the system-friendly option, and you, as an investor, you will only do this if you benefit from the benefits that society has. So, where do we have the policy implications of this? So what this work I think tells us at a very high level is that policy should acknowledge, and not verbally, but in terms of policies and market design, value differences. The economic value of renewable energy and other energy depends on technology, design, and location. So policy frameworks and market design should not seek to get the cheapest RE, but that RE that has the highest net benefit for society, and that can be different. And certain support policies comply with that requirement, like renewable portfolio standards, or what Europeans call feed-in premiums, and others do not. Feed-in tariffs, traditional feed-in tariffs do not. Disregard this best practice. That was for a German policy audience, so that's I had to tell them that Germans are great. And sort of feed-in premiums and portfolio standards ensure that the scarcity signals from markets are seen by investors. A feed-in tariff sort of makes makes the market invisible to investors, but feed-in premiums and RPSs allow market signals to be seen by investors, but then the market signals need to be right. Then the market signals need to be correctly displaying scarcity, both in space and in time. And that implies that, for example, renewable energy producers should be exposed to the cost of forecast errors and to the cost of connecting the assets to the grid, because only if they're exposed to these price signals, they will pick the investment option that minimizes these costs. That's what I have on this slide, pretty much what I just said. So let me conclude the last 3 minutes. What I take away from these 5 years of research and this series of papers. First and most fundamental is the observation that economics has two sides. And as basic as this observation is, it's often forgotten in the debate. And that's true for wind power, that's true for solar power, but that's true for all other energy sources, and that's true essentially for everything in life that you evaluate economically. It has a value and it has a cost, and you need to compare those. Just comparing cost of coal versus cost of nuclear versus cost of solar versus cost of wind doesn't tell you anything. Second, that comes from a paper that's in the appendix that I haven't talked about much here. You can show analytically that in some sense it's the fluctuation that determines the speed of the drop. If you have two turbines and one fluctuates more than the other, the more fluctuating will cause a steeper loss in value. In that sense, it's the variability or intermittency that causes the value drop. As a corollary of this, having large scale, 50, 70, 80, 100% deployment of renewable energy will be more difficult, more tricky to achieve. In that sense, this is all bad news. And this is because it's not sufficient for wind energy to become cost competitive to coal plants. You need to be cost competitive and compensate for the value drop. So you need to have costs that are significantly below coal plants to compete with coal plants. While coal plants should pay for their emissions, but that's another story. The size of the value drop depends. It's not a fixed parameter. It depends on the circumstances, on the power system, but it also depends on technology. So some of the technologies, as we've seen, what we call low wind speeds or advanced turbines, have much less of a drop. And funny or not so funnily, carbon pricing can have a negative rather than a positive impact under certain conditions. That's the investment channel that we discussed briefly earlier today. And the message to policymakers, one of the messages is that prices and policies should ensure that investors can actually see the differences in value that their output, that their assets have. Papers are linked. They're all open access. Four of them are published. One of them, this is a working paper that we've tried to publish for quite a while. But thank you very much.
All right, we are at the top of the hour, so I know